Hello everyone, and welcome for this third week of the course of networks. And well, today what we're going to do is to consider different types of models of graphs. So let me first say a few things about what I mean by a model of a graph. And typically in the literature, you can distinguish between two different types of models. On the one hand, you have random graph models. In a random graph model, what you do is you are basically assuming that each edge is a random variable subject to certain constraints. And important examples would be the Erdős-Rényi graph, be the one that we're going to be looking at in this video. There's also the configuration model that you're going to be seeing in the next video. And in each case, what you do is, so you have this random graph obtained by combining all of these random edges. And the thing is that the model doesn't try to explain why we have certain values for the parameters, for instance, the degree. It doesn't either try to explain why there would be some constraints that are applied in order to define the graph. But instead, what it is good for is to be used as a baseline in order to compare some empirical observations from the ones that would be emerging purely by chance, basically. That would be the purpose of these random graph models. Now, there is also another type of model that is very popular in the literature, and it's the case of mechanistic models. In the case of mechanistic models, you really think about the mechanisms that may have led to the evolution of the system as you see it now. And typically what you do for mechanistic models is to come up with some simple rules on the way nodes and edges are added or removed from the system. And you try to predict what kind of network would emerge from these simple rules. And if you compare the graphs that you observe empirically with the graphs that are generated by these models, well, you may find some potential forces, candidates for forces that may have been driving the evolution of empirical networks. So in a way, the first two videos of this week are going to be focusing on the first family of models. We'll do the Erdős-Rényi network now. We'll do the configuration model just after. And in the third video of the week, we'll be looking at mechanistic models and more specifically at a model called the Barabasi-Albad model. But let's start indeed with the Erdős-Rényi model. So Erdős-Rényi model. Well, Erdős and Rényi are two very famous mathematicians, Hungarian mathematicians, who have been producing wonderful contributions in different areas of mathematics in the 40s, 50s, 60s. But together, so they came up with this idea of a model of a random graph. It was proposed in 1959. So it's typically called Erdős-Rényi model, but it can also be called the Poisson. It reminds us of Poisson processes, or a binomial random model. So how is it defined? So the model is defined as it's a model of a graph that takes as two parameters, n, the number of nodes, and q, that is a probability. Now, the probability q is basically the probability that a link exists between any pair of nodes. So, so the graph is built in such a way that there are no self-loops. Self-loops are excluded. What you do is that for each pair of nodes, you consider it as a Bernoulli process with a probability PQ, and either you generate an edge between these two nodes or not. And each pair of nodes is going to be independent. Now, if you think about a model like that one, well, clearly, as long as 0 is smaller than q is smaller than 1, well, depending on the outcome of the random processes, any graph of n nodes could be generated by that process. Yeah? It could happen, let's say that n is 4. It could happen that this graph is generated. It could happen that that graph here is generated, and anything in between has a certain priority to be generated, depending on the outcome of each of the random processes. So that's why when you think about a random graph model, you shouldn't think about one graph. You should think of an ensemble of graphs. And you should think of all of the graphs that in this case have n equal to 4, and on the way the probability is going to be shifted towards certain graphs versus certain others. And typically when you look at random graph models, you don't try to estimate the probability of one graph, obviously. What you try to do is to estimate the statistical properties over that ensemble of graphs. And typically, you try to find, for instance, what is the average value of a certain measure, or also the variance or the fluctuations around that average. Now, because the Adder-Shreni model is such that each edge is independent and that the probabilities are uniform, well, many of the properties of that graph, of that ensemble of graph, can be calculated. So for instance, a first thing is that because the probability of generating a network with m links is going to be given by a binomial distribution. So we have the probability to generate a graph that is such that we have exactly m edges. Well, it's going to be simply given by a binomial distribution, where we have basically to choose between the n minus 1 over 2. This is the maximum number, the total number of pairs for which we need to generate a random number. We take m of those, and then of course we have a probability q to have it positive and 1 minus q to have it negative. N minus 1 divided by 2 minus n. So it means that we already know that the probability to have a graph with exactly m edges is going to be given by this expression over here, from which we can find that the expected number of edges in this ensemble of graphs would simply be given by q times n minus 1 divided by 2, which is again a very intuitive result. Now, what about the degree distribution? Well, we can use exactly the same trick to estimate what is the probability that a node has exactly k connections. It's going to be equal to, well, we have n minus 1 possible connections for a node. We need to have that k of those are positive, and we get basically the binomial distribution that naturally emerges for the degree distribution. That's wonderful. We have the binomial distribution coming here. And from there, we can find that the average degree is going to be equal to a q times n minus 1. Now, the thing is that, well, typically, the Adder-Shreni model is defined for sparse graphs. So it means that we would like that the average degree doesn't depend on the total size. We'd like to be able to fix the average degree independently on the total size of the system, which means that typically one tends to rescale the Q as 1 over n in order to make sure that there is no size dependency of the average degree of in the graph. Now, in situations when this number q equal to average of k divided by n minus 1 is sufficiently small, we basically have the binomial distribution will be well approximated by a Poisson distribution, in which case we have the P of q is going to be equal to the average of k to the power k divided by k factorial exponential of minus average of k. And so that's why we call this model either the Poisson model or the binomial model or the Adder-Shreni model, basically. So very good. So there are plenty of things that can be shown for the Adder-Shreni model. So here I just enumerate a few of them. So for instance, the average distance between n pair of nodes is going to be behaving like the log of n divided by the log of the average degree. So it means that the dependency of the average distance between a pair of nodes on the total size is logarithmic, which in itself explains this small world behavior, that even if you multiply the size of your system by 100, well, you would just have this 100 will go into logarithmic dependence, and it will only weakly affect the distance between any pair of nodes inside the system. Something else that is also important to note is that the clustering coefficient is going to be equal to the average degree divided by n minus 1. So it means here that when n becomes sufficiently small, we'll have that this quantity here goes to 0. So it means that for the Adershoни random graph model, we have that the density of triangles goes to 0. This is something actually that has quite a few implications, because it means that locally, if you look around a node, you will have 0 triangles around it. So it means that locally, the system is tree-like. We'll have that if you look at the local behavior around nodes, the system basically behaves like a tree locally. And this is actually a property that is used and exploited in many works on dynamics, where you often exploit this locally tree-like structure in order to approximate the dynamics taking place on random graphs that would be generated by the Adershoни model, for instance. Now, these would be here like two simple properties. Now, there is a property of the Adershoni graph that is actually quite powerful because it's so general. And this is the fact that the Adershoni random graph exhibits a phase transition in its connectivity. So let's focus on the following question. So let's assume that we are interested in the size of the largest connected component. Yeah? And we ask what would be its dependency on the mean degree average of K. Well, clearly, if I have here I plot here the size of the largest connected component divided by n, right? So that everything is between 0 and 1. And I have my average degree here. When the average degree is large, we can be sure that every pair of nodes will be, every node will be connected to every other one, right? So it means that we know that when the average K is large, we should be close to 1. On the other hand, when average K is equal to 0, well, we basically have that each node is its own connected component, and the size here should be 1 over n. When n is large, it means that we should have something that is close to 0. So it means that we go from the two extremes, from 0 to 1. And the question would be, how do we go from these two extremes? Well, the thing is that we will not go there in a smooth fashion. Instead, what will happen is that we will have a very nice transition taking place and a critical value of the average connectivity, such that when you're below that value, you will basically have that there are no large connected components in your graph. And after it, you will start to see the emergence of giant components inside your system. So just before we go into the math, let me show you what we will be observing actually. Well, we will observe exactly something like that, so we have this mean degree. What we will observe is that when the mean degree, we have critical value, it's equal to 1. When the average degree is smaller than that 1, we will have that the graph will tend to become composed of a large number of extremely small connected components, each one looking like a tree. When we go above 1, we'll basically have the formation of a giant connected component. Of course, there might still be some smaller ones next to it. And of course, the giant component will become larger and larger and larger as the average degree is increased. And if you want to know what's happening exactly at the transition, and this transition is called the percolation transition, where at that point, actually, it can be shown that we have that, if you do an histogram of the size of the connected components, it will look like a power law distribution. But this is not something that we're going to be seeing today. So let's try to understand why we expect such a transition to take place at the value of 1. Okay. And let's do the math. So, and again, we'll be using and exploiting the independence between any edge in the system. So here, what we do is we consider the probability that a randomly chosen node does not belong to the giant component, if it exists. And we write it as U, okay? Now, once we have this, it means that if a giant component is absent, if there is no giant component, it means that U is equal to 1, yeah? No giant component, U is equal to 1, and else it means that U is going to be smaller than 1, yeah? Now, by definition, so if we take a certain node I, so take a certain node I, and if it does not belong to the giant connected component, well, it must it cannot be, well, so if a node I does not belong to the GCC, it basically means that it cannot be adjacent, to any node J, which is itself part of the giant connected component, right? Otherwise, it would be part of it by definition. So it means now that if we take a certain node I and a certain node J, whichever it is, we have two possibilities. Either I, either I is not connected to J, yeah, or I is connected to J, yes, but J does not belong to the GCC. Yeah. So if we have a node I that doesn't belong to the giant connected component, and we take another node J, well, either I is not connected to J, we don't have any problem, else I is connected to J, but we need to make sure that J is not part of the giant connected component. So this first part takes place with a probability 1 minus Q. This one here takes place with a probability Q times U. Yeah. Now, this is what's happening through the node J, right? But we need to have that, and through this node J, we basically have that the probability that node I does not belong to the giant connected component through node J is going to be obtained by 1 minus Q plus Q times U, right? Now, because this node I could be connected to any of the node J's, we need to impose this condition n minus 1 times, because there are n minus 1 nodes through which it could be connected to the giant connected component. And so it means here that we need to have that this quantity here to the n minus 1 is going to be simply equal to the U. So the probability that node I is not part of the giant connected component is actually satisfying this relation due to the fact that it cannot be connected to any other node that is itself part of the giant connected component. And we obtain here a self-consistency relation for the variable u that we need to solve, basically. Now, what we're going to be doing here is we're going to be taking the limit when n goes to infinity of, and we know that the limit of this minus x over n to the power n is equal to exponential of minus x, which gives us that the relation is equal to u is equal to exponential of minus average of k times 1 minus u. And now what we do is we're going to be changing variables. So we'll be defining the probability S that a node belongs to the giant connected component, which is such that S is equal to 1 minus u. And if you plug this into the previous equations, we obtain that the S needs to satisfy this expression here. What we need to look is what are the values of average value of k that are such that we may have some non-trivial solutions to that problem. So if you try to plot it, well, what's going to happen is that what you need to do is to look for, well, we're interested in positive values of S. We are looking at the intersection between S, right, and 1 minus the exponential. And this 1 minus the exponential actually is going to be always bound between 0 and 1. And actually, when the average of k is small, it's going to be behaving like this. When the average of k is large, it's going to be behaving like this. And so we see that it always has 0 as a solution, right? But we have the possibility for a second solution to appear. And this happens in situations when the orange curve grows faster than 1 at the origin. Yes? If it grows faster than 1 at the origin, after that it's going to bend and it's going to be meeting the curve S, which basically gives us a condition we need to impose, basically, that d by ds of 1 minus exponential of minus ks is equal to 1, which is actually equal to the average degree. So basically, this gives us our result. What we have here is that when we have a critical value, this critical value is when the two curves are exactly tangent of each other. And what you obtain here is that if the average degree is sufficiently small, there's just one intersection point, we just have S equal to 0, and there is no giant connected component. And what's happening is that the graph is made of many small components. While if the average degree becomes larger than 1, we have the possibility for a new solution to emerge, and we have the formation of this giant connected component that is going to be basically made of a non-negligible part of the whole system and attracting a large part of all of the nodes that are present in the system. We have this nice phase transition, which is usually called the percolation transition. Now, something important to keep in mind is that, of course, here we have like a quantitative prediction. The transition will take place when the average degree is 1. Well, in real life settings, when we look at real life data, it could happen that that transition takes place for other values. But nonetheless, in almost any empirical data and any random graph model, we will always have that if we start to take edges randomly, we will go from a big connected component and then suddenly it's going to be breaking apart along the kind of transitions that has just been obtained from this Alderson-Renyi model. So it means that it provides us from some insights on the kind of collective behavior that can take place in a real world network, despite the fact that it's such a simplistic model. So I think that would be concluding this first video. In the next video, we'll look at a slightly more complicated model called the configuration model. So hello everyone, and welcome for this second video, where we'll be looking at a generalization of the Erdős-Rényi model that is called the configuration model, and we'll talk about its potential use for motif analysis. But just before we start, so if you remember what we've seen with the Erdős-Rényi model, we've seen that the degree distribution is going to be a binomial or a Poisson distribution. And this is actually like a property that is very far from what is observed in empirical data. To show you so, here are three examples of graphs, where in red you have the histogram of the degrees, that would be the degree distribution from the empirical data. And in black, I've been plotting the Poisson distribution that would have exactly the same average degree. And as can be seen in each of these examples, what we have in red here, right, is going to be very different from what we have from the model. And in the model, we have values that are very much concentrated around the average, while in empirical data, we'll have much more variability associated to the kind of parabolas that we'll be expecting, as we've been discussing before. Yep. So it means that at least one of the properties of the Erdős-Rényi model is very much unrealistic, and that would be its degree distribution. Well, one way to circumvent this limitation is to generalize the model, and one such generalization is the configuration model. So, configuration model. So what is the configuration model? In the configuration model, what you try to do is to generate an ensemble of graphs having a certain degree sequence. So you fix the degrees of all of the nodes, and you try to, and then you consider the ensemble of graphs that are such that the nodes will have these prescribed degrees. And of course, if you do so, if you fix the degrees of the nodes, you can clearly fix the degree distribution, which basically means that through the configuration model, you can have a random graph model where you can tune the degree distribution and choose it to be whichever it is. And this flexibility is something that people have been using quite a lot, also because it allows them to have heterogeneous graphs naturally. And that's one of the reasons why the configuration model is used in most applications as a baseline in order to compare real-life data with what would happen by chance, given the fact that the nodes have certain degrees. So how do you generate such a configuration model? Well, typically what you need to do is to define a certain degree sequence, Ki, for all of the nodes. And these degrees could come from empirical data, for instance, or they could be generated from a certain degree distribution, imposing that the sum of the degrees would be an even number in order to satisfy the handshaking theorem. Yes? And once you've done so, well, then you're going to be, let's assume that this node is a degree 3, that one is a degree 2. It looks a bit like this paradox that we mentioned a few weeks ago, last week actually. And then this one would have a degree 2, 4, 2, that wouldn't be okay. We have another one with 1. And what you do is actually you consider each node with half edges, and then you're going to pair all of these edges randomly until nothing can be done. Well, if you are to do an operation like that, and in this case, I would have done it with the degree 3, 2, 2, 1, and the sum of the degrees is indeed equal to 8, which is perfectly fine. Then from there, those would be 3 graphs from the ensemble of graphs that would be generated from this degree sequence. So what you can see here is that, well, there would be situations where you would have self-loops that could happen, and others where you would have multiple edges that could happen. That was not the case in the case for the Ardashani random graph. Well, in the case of the configuration model, these configurations may happen, but actually in a practical case, like in a practical setting, that wouldn't be very much important. Indeed, it can be shown that if you have a sufficiently large graph, you will have the density of such self-loops and multiple edges go to 0. And so it means that in practice, you can simply generate graphs, and once it's been generated, you look for self-loops and multiple edges and take them out. You may lose a few edges, but not so many, and hence you can generate very easily an ensemble of graphs that are having an imposed sequence onto the grids. Now, there are also many things that can be shown about the configuration model. And one such property is a property that is going to be very important later on when we'll be looking at modularity and clustering graphs. And that would be the following question. What is the expected number of links between a certain node I that has a degree ki and a certain node j that has a certain degree kj? Well, when you think about it, so let's take a certain node I and take one of its half edges. Well, clearly, if this is the kj here, well, if the node j has many edges, it will be more likely that I connects to j than if node j doesn't have many edges, right? And clearly what we'll have is that that edge is going to be connected to one of the edges of j with a probability that is proportional to kj divided by twice the number of edges. It should be -1, but the -1 is very small when m is large. Now, if you're interested in the expected number of links between I and j, well, you need to do this calculation for each of the possible edges that leave I. And what you arrive at is that the expected number of links between node I and node j in the configuration model would be equal to the product of ki times kj divided by twice the number of edges. Which basically means that if you have two nodes that are such that the degrees are high, they will be even more likely to be connected than two nodes whose degrees are very small, which is something very intuitive. And actually, this quantity here is something that we're going to be using quite a lot, I think next week, when we'll be looking at the notion of modularity. So try to keep this in mind. Now, there are other properties that can be shown about the configuration model, including the fact that its average distance is going to be very small as well, that its clustering coefficient is also something that is going to be vanishingly small when the graph is sufficiently large. So it means that, again, this is a very simple model for which we can derive quite a few properties analytically. Now, what I would like to talk about now is something that is slightly different, and it's how can we use this configuration model in a statistical setting in order to try to assess whether or not certain properties of an empirical graph are significant or not. And this is something that people do a lot, usually, when they consider motif analysis. So what is motif analysis? In motif analysis, what you try to do is to estimate if certain motifs that you observe in a graph are significant or not. So, as an example, let's consider the case of 3 node motifs in a directed network. So there are 13 different types of motifs that can be defined in such a in such a directed network. And let's assume that you observe the first one 5 times, the second one 17 times, the second one 18 times in an empirical graph, maybe this one once, this one 15 times, and so on and so forth, right? How could you decide, how could you assess which are the significant motifs and which ones are the insignificant ones? Well, clearly, let's assume that you tend to observe that number one is very, very much very abundant. Well, actually, it could simply be abundant by the fact that the graph is poorly connected. Yeah? So it means that it might not be that that motif is particularly abundant. It's just there because that motif has few edges, yes? And if the graph is poorly connected, well, motifs with few edges are expected to happen more often than those with a large number of edges. Yeah? And so it means that if you want to assess whether or not a motif is important or not, well, you need to be able to compare their frequencies with the frequency that they have in an empirical data with their frequencies in randomized versions of the data, which is exactly what people do, usually by using the configuration model. So how do they do that in practice? Well, in practice, they would construct a generalization of the configuration model for directed networks, where instead of fixing Ki, they would fix the Ki in and the Ki out. Yes? And so they would have an ensemble called the directed configuration model, where you fix the in and out degrees of each node. And then they would simply count. Let's assume that you have a certain subgraph M. Well, you will be counting the C of M, the frequency of that subgraph in empirical data. And then, in order to assess whether or not this number is large or small, you're going to be calculating this C tilde of M from the directed configuration model. So for instance, you do it 1,000 times for 1,000 realizations of a graph that will have the same the same number of nodes, obviously, and where the degrees will have the same in and out degrees as in the empirical data set. And if you do so, well, you can then calculate an average in this ensemble and also standard deviation from that ensemble. And you can construct relatively easily a z-score that will basically tell you if you are very far or very close to what would happen in the case of a randomized data set. And so typically, if the z-score is very large or very positive or very negative, that would be associated to statistical overrepresentation or statistical underrepresentation of certain motifs. And this is actually the essence of motif analysis, a field of science that is very, well, a field of research that's very active, especially in biology, where people try to find certain building blocks that may have some biological nature or might be associated to some biological function. And by observing their anomalous statistical representation, you may find out you may find out groups of nodes that may actually have a function together through this motif analysis. That was actually one of the earliest motivation for this type of study. So, well, this was just an example of how to use the configuration model. It can be used not only for motif analysis, but actually for any kind of interpretation of analysis of that is done on real-life data. And we will come back to that later on when we will be looking at the problem of clustering. So thank you very much. So hello everyone, and welcome to the third video of the week. We will be looking at another type of model that people use in order to model networks. So the first two models we considered were random graph models, where for each case, edges between pairs of nodes were seen as random variables. here in this case, we'll be looking at it from a very different point of view. And we'll look at it from a mechanistic point of view, where we try to find some simple mechanisms and then observe the kind of networks that are generated by these mechanisms. And if the graph that you obtain look like the ones that we have in real life, well, it could be because actually this mechanism was one of the driving force behind the evolution of the real-world network. The model that we're going to be considering is something called the preferential attachment. So what about these models? Well, there are many situations when networks are not static entities, and where they tend to grow in time. So very good examples would be citation networks. There are papers published every day citing previous ones. And so it means that, seen as a graph, you will have that the citation network is growing in time. Similarly, social networks are also evolving entities. But of course, you may have that certain edge appear, others disappear, but clearly this would be a very dynamical entity. Now, in the class of mechanistic models, one of the most popular ones, partly because it's one of those where you can really do calculations relatively easily, is the one of growing networks, where the network can only grow and where the links, once they are present, will be there forever. So we'll be looking at growing networks, like citation networks, for instance. And the network that we'll be considering is actually a model that has gained a lot of popularity at the end of the 1990s. It was proposed by Barabasi and Albert. And as you see, that's a very simple model, and it gained a lot of popularity because it could explain why, or at least it could provide one explanation why real-world networks tend to have very fat-tailed distributions. Now, the model is usually called the BA model for Barabasi and Albert, or the preferential attachment model. Actually, was not so new. It's been discovered afterwards that it was basically a reinvention of models that were existing before. And that model is part of the big family of multiplicative models that date back from the works of Polya, for instance, of Yule, but also of the works of Robert Merton, who talked about the Matthew effect, and of the work of Herbert Simon, who was interested in the way wealth would be spread heterogeneously in populations. In our case, it wouldn't be wealth, it would be degrees. Okay? So how is this model defined? Well, this model is defined basically as follows. So we start from a configuration with M0 nodes, and typically we take them fully connected with each other. Here we have 3 nodes that are connected with each other. And then at discrete times, at each time, a new node arrives with some potential connections. So here in this case, it will always have 2 connections every time it arrives. Now, the key is that when a node arrives, there will already be n prime nodes with degree sequences ki. We'll have that a new node, when it arrives, connects preferentially and proportionally to nodes with high degrees. So it means that if I arrive and I have to choose between a node of degree 1 and 2, my probability to connect with a node of degree 2 will be twice larger than with the one of degree 1. And you see that this leads to some sort of reinforcement, multiplicative effect, where the high degree nodes will receive more connections, and it will lead to the formation of heterogeneities in the system. And so here, this is encoded by the fact that the probability that a node connects to a node of degree ki is going to be proportional to the degree and divided by the sum for I going from 1 to n prime to the sum of all of the degrees that are already present in the system of the kj's. Yeah. So it means that you connect proportionally to the degree of the nodes that are already present in the previous step. So this is a possible configuration. I started from here. After one step, I arrive at this configuration, and then that one, and so on and so forth. And so, of course, errors or fluctuations will have an effect in the course of time. That's why it's a stochastic model. But nonetheless, well, certain properties of the graph will be robust, and we'll have that certain of the statistical properties of the graph will be predicted and will actually be representative of the ensemble of graphs that are generated by this kind of process. Now, one such property that is very robust and can be predicted is the degree distribution, the P of k. And it can be shown, and we'll see in a second, that actually it will be such that it will generate the degree distribution such that the tail behaves like k to the minus 3, like a power law. So, as I said, it's one of the reasons why such a model gained a lot of attention at the end of the 90s. And even now, when people want to generate graphs that are such that they have a very fat degree distribution, well, they could use an algorithm like this one here, because it's extremely simple, extremely easy, and it generates very fast networks that have a certain prescribed degree distribution. So how could we show that? How could we show this property here? Well, the way to do so is by means of a master equation. So what we'll do is to consider the probability that a certain node that arrived at the system at the time ti will have a degree k at time t. So probability that a node I arriving at ti has degree k at time t. And if you write down the master equation, it looks very much like the ones that we've been writing looking at Poisson processes or random walk processes. What we'll get is that this P of k ti t plus 1 is equal to k minus 1 divided by 2t P of k minus 1 ti t plus 1 minus k over 2t times P of k ti t. And what we have that this quantity here is simply the probability that the node I did not receive an edge at time t, while that one here would be the probability that the node I at the degree k minus 1 receives an edge and hence has a degree k afterwards. Okay? So once you get that expression, well, you can then define the degree distribution, the asymptotic degree distribution P of k, to be equal to the limit when t goes to infinity of the sum over the ti's, of the sum of all of the nodes that have arrived in the system, basically, of this probability of having k when you arrive at ti at time t, and divided by t. And why do you divide by t? Well, because basically, well, you have, well, as time goes on, you have more and more nodes coming in, and hence you need to divide by that number of nodes in order to have a properly defined degree distribution. So if you take that expression here and apply it to what we have just before, after a few lines, and this is something that you can find in the notes, you will arrive at the fact that t plus 1 times P of k is equal to k minus 1 divided by 2t times t P of k minus 1 plus 1 minus k over 2t times T times P of K. And if you rearrange the terms, what you obtain is that P of K is going to be equal to K minus 1 divided by K plus 2 times P of K minus 1 for values of K that are actually larger than M plus 1, where M is this number of edges of the nodes when they arrive in the system. And well, this is a very simple recursive equation to solve, right? And if you solve it, you obtain that the P of K, the degree distribution, is going to be equal to 1 divided by K, K plus 1, K plus 2, which basically behaves like K to the minus 3, which is indeed a degree distribution that would behave like a power law. Now, of course, models like those are not as statistically sound as the random graph models, but as I said, they have one advantage. And that advantage is that they can help you to translate what is the effect of a mechanism onto the structural graphs. In this case, the mechanism is preferential attachment, the fact that the graph is growing and that high degree nodes are more likely to receive edges. And this translates at the organizational level into graphs that tend to have broad degree distributions, and in this case, power law degree distributions. So I really encourage you just to try to code such a graph model. It's very easy. You can relatively easily generate graphs with broad degree distributions. It's good fun, and you can check at the same time that the theoretical predictions are correct. So, well, that would be the end for this last video. So I thank you all for your attention, and I look forward to seeing you next week.